Alright, welcome back guys. So I took a short little break and we're going to try to finish up 4.2 now. Okay, so you've just seen how, I guess, inconvenient it is when you're trying to find a probability that x is greater than some number, less than or equal to some value. Because you end up having to calculate the probability that x is different specific values and then adding those probabilities together. So we're going to try to remedy that using this cumulative probability function or density function. Okay, so cumulative binomial probability. So think of the word accumulate. You know, if you're accumulating wealth, that means you're adding it up, right? You're just kind of accumulating it. So what if you want to find the probability that there are at most x successes in n trials? So we just saw an example of that, didn't we? So for example, what is the probability that in 10 flips of a coin there are at most 3 successes? So this just means what's the probability that x is either 0 or 1 or 2 or 3, okay? So like I said, I think there may be a mistype right here, but you could find all these individual probabilities and add them all together and do it that way. But there's also this binomial CDF function in our calculator, and I showed you this earlier in the part 1 video, and I'll go ahead and show it to you right now. So you're going to access it the same way. You're going to second variables, and it's below the binomial probability density function. It's this one right here. And so what this one does, guys, is it basically, you're still going to need to enter the values for the parameters n and p, and then when you enter a value for x, you're not entering a value for just that specific number. You're entering values for x up to and including that number. Okay, so that's why this function is so useful, so helpful here. So see, this feature calculates the sum of all the probabilities up to and including the value for x. Okay, so let's look at an example here. It says 39% of U.S. adults think that the government should help fight childhood obesity. You randomly select 6 U.S. adults, so find the probability that the number of U.S. adults who think that the government should help fight childhood obesity is exactly 2, at least 4, and less than 3. Okay. Well, we can go ahead and find this binomial probability distribution. Okay, we could complete this, but we could also use that binomial cumulative density function. Let's go ahead and define the values for our parameters. So in this case, if we're selecting 6 adults, n is going to be 6, and we're going to deem the respondent answering yes to the government actively fighting childhood obesity as a success. So that corresponding probability would be 39%, okay? And so you could find these the same way if you go to your y equals screen and put this in. I think this one I actually did in Excel right here, so you can see I gave n a value of 6, a probability of success, a value of 0.39, and then I put in these 7 different values for our random variable, and then these are the corresponding probabilities. And the way I did this, guys, is what I showed you in part 1. Okay, so use that binomial distribution, and I'm just referring to different cells here. So I'm telling it for my value of n to grab whatever's in this cell, for my value of p to grab whatever's in this cell, and then for my changing values of x to grab these corresponding values of x. Okay, so that's, anyway, you don't have to know all this, but these are the values that you would get. Okay, we'll go ahead and copy these into our table. You can see that these appear to be rounded to 5 decimals. Well, I'll say that more like 6 decimal places, most of them anyway. And 97636. And then when x is 2, our probability is 0.315893. When x is 3, okay. You can see now the probabilities are starting to trend downward. And they actually have been for values of, starting at values of x equals 2. These probabilities are going downward. And the reason is because the probability of success is about 40%. So you wouldn't expect this many successes in 6 trials. So that's why these probabilities are really starting to decline. You would expect about 40% success, essentially. Well, I put an extra 0 in there. Okay, I'm going to say that I used Excel. Okay, you can just as easily use your calculator if you want, the way I showed you in part 1, to find these, or you can just do them individually if you want. Okay, there's no wrong way to do it. All right, now to actually answer this, part A. The probability that x is equal to exactly 2, okay? So that there would be exactly 2 individuals surveyed that would say yes, they think the government needs to be actively involved in fighting childhood obesity. Well, the probability that corresponds to x equals 2 is, I'm going to round this to 3 decimal places, so 0.316. Okay. Now for part B, it says at least 4. So that means 4, 5, or 6. So I could write it, I could express it this way. The probability that x is greater than or equal to 4. Okay, so that would be the same as probability that x is equal to 4 plus probability that x is equal to 5 plus the probability that x is equal to 6. Okay. Now we could, look at this table or find these and add them together individually. You know what? I think let's hold off part B just for a second. Let's try to tackle part C first, and then we're going to go back to part B. So part C, we want to find the probability that x is less than 3. Well, x less than 3 really means that x is less than or equal to 2, okay? If it's less than 3, it means it's less than or equal to 2. That means the 2 is included. And you may be wondering, why would I express it this way? Well, because if we're going to use this binomial, this cumulative density function, then it says it calculates the sum of all the probabilities up to and including that value for x. Okay? So I can use the binomial CDF, and n is 6, p is 0.39, and x is the highest value. Okay, so in this case it's 2. So, you sort of want to be careful here, guys, because x less than 3 means that x doesn't take on a value of 3. So you have to write it like this. So that value of x is going to be 2 instead of 3. All right, so let's utilize this function real quick. So I've already got it selected right here. Okay, so the total number of trials is 6. The probability is 39%, and we want to find the probability that x is less than or equal to 2. I'm going to paste this, and then hit enter. We're going to get this value. And if you notice, this value is close to what it would be if you had added up these values right here for values of x from 0 all the way to 2. Okay? In fact, if you add these up, you should get this. So this to 3 decimal places is going to be roughly 0.565. Okay? All right, now having done that one, and come back to part B. So part B says at least 4, so that means 4 or bigger. Well, that binomial CDF, it only would give it, if we use it, it only give us the probabilities of values of x that are 4 or less, not 4 or bigger. So maybe I could figure out a way to restructure this, implementing the idea of a complement. Okay, so the opposite of x being greater than or equal to 4 would be that x is strictly less than or equal to 3. Okay, this would be the complement. Actually, maybe I should write this somewhere else. So finding the probability of x being greater than or equal to 4 is really going to be the same as finding the probability that x is less than or equal to 3 and subtracting that from 1, okay? Because this event right here is the complement of this event. And defining the problem like this, trying to figure out the probability that x is less than or equal to 3, that will allow me the opportunity to use that binomial CDF function, okay? So I'll go ahead and write this out again. This will be 1 minus the binomial CDF. And then those parameters are the same. N is still 6. P is still 0.39. But x is now 3. Okay. So P and x. All right, so I can use my calculator. Let's get it. So guys, what we could do, since I've already got the binomial CDF function in there, is I can just use that entry. And I can replace that value of x with 3. Okay, and then I can hit enter. All right, so this is the probability that x is less than or equal to 3. Well, we're trying to find the probability that x is 4 or bigger. So we can use that idea of a complement. So I can say 1 minus the probability that x is 3 or less will give me the probability that x is 4 or greater. Okay. So to grab that previous one, I'll just hit second and then answer right here and hit enter. And this is going to give me a value of, if I round this to 3 decimal places, it'll be 0.166. 0.166. Okay. All right. So like I said, there's not a, well, there's definitely a wrong and right way to do these, but there are some approaches that are more time consuming than others. Okay, if you hit 1 and 2, you could have, like we did in those previous examples from part 1, we could have found the individual probabilities that x is equal to 4 and then to 5 and then to 6 and then added them all together. Okay, but I'm trying to think outside of the box a little bit, because remember, the whole idea of well, if you remember, sometimes it's easier to, instead of calculating the probability that an event will occur, it's actually easier to calculate the probability that the event will not occur, and that's essentially what we're doing right here. Okay, so anyway, before we move on to, I pasted this in the notes. This is what a probability distribution would look like. Okay, so these, the heights of these bars represent the relative probabilities that x would assume any of these 7 different values. So you can see most of the probability lies right here at 2. And so that is close to the expected value. You would expect that around probably between 2 and 3 respondents to answer yes to that particular survey question. And that really has to do with the probability that they'll say yes. Okay, that's why most of the probability is focused right here in the middle, because 2 and 3 out of 6 is somewhere around 40%, 33%, 40%, something like that. But anyway, you can see kind of how the probability decreases as x gets larger. See, whenever x is 6, that would be a rare event that all 6 participants would say yes, if only 40% of the population thinks that the government should be actively involved in fighting childhood obesity. But anyway, I just wanted you here to have been able to see what a probability distribution actually looks like. So it's really just a histogram, isn't it? All right, let's knock out this last little part. Okay, so one of the nice things about working with binomial distributions is how easy it is to find the mean, variance, and standard deviation. So if you recall from 4.1, I actually did a lot of that by hand. I had to make a table and find, of course I used technology to find all the individual values, but I had to copy all those numbers, and that was very cumbersome. And it creates opportunity for error, okay? Fortunately though, guys, finding the mean and the standard deviation with these binomial distributions is quite easy. To find the mean is just the number of trials times the probability of success. And I think this makes sense intuitively. So for example, if you think about that LeBron James example that I gave in chapter 3, if LeBron James is maybe a 70% free throw shooter, and in one particular game he goes to the free throw line exactly 10 times, you would expect him to hit 70% of those shots. So 70% times 10 is 7. Okay, well that's what this says right here. It's the number of trials times the probability of success for each of those trials. And then the variance is very similar. You're just going to end up multiplying the mean times whatever Q is. And then as always, to find the standard deviation, it's just the square root of the variance. Okay. All right, so let's go ahead and look at example 6 here. It says in Little Rock, it rains on about 30% of the days in November. So find the mean, variance, and standard deviation for the number of days of rain in November. So by the way, this is binomial because a success would be that it rains. And each day would be like a trial. Okay, so there's like 30 days in November, so there'd be like 30 trials. And so how many of those trials would yield a success on average? Or in other words, how many of those days in November could we expect there to be rain? Well, find the mean, it's just going to be the number of trials times the probability. So in this case, 30 days times 30%. And guys, that's going to give us 9 days, okay? So we would expect that on average, it would rain 9 days in November. Now, this is on average, right? And you know how these probability distributions are. There'll be probabilities associated with other values of x, like there will be a probability associated with x equals 30, meaning that it rains every single day in the month of November. Now that associated probability would be extremely low, because that's very unlikely to happen. But nonetheless, there would still be probability there. All right, and then to find the variance, this is just going to be n times p times q, which would be 30 days times 30% times 70%, right? And what would this be? I want to say that it's 0.63. Let's see. Yeah, 6.3. Now, I do want to point out, this would be in square units. That's another reason the variance is not used as a useful statistic, okay? Because the units are always going to be squared. So the more useful statistic is the standard deviation, as you guys know. So the standard deviation is going to be the square root of that, or in other words, the square root of 6.3. So if you take the square root of a unit that's squared, you'll get just that unit. Okay, so I'm going to round this to 2 decimal places and call this 2.51 days. Okay, so let's talk about what this means just for a second. So this is the standard deviation. So think about, we were talking about symmetric bell-shaped curves or distributions. We could expect, and we'll talk more about this later, how the binomial approximates the normal distribution, but we could expect that about, if you remember the empirical rule, about 68% of the time, the number of days that it rains in November will be 6.3, give or take 2.5 days. Because that would be 1 standard deviation below to 1 standard deviation above. And then we could extend that. We could say, well, 2 standard deviations would be about 5 days. So we could say about 95% of the time in the month of November, it's going to rain anywhere between, well, this wouldn't really make sense here because, yeah, it would. 5 days below the mean, which would be 1.3 days, to 5 days above the mean, which would be 11.3 days. So within that interval, we would have 95% of the distribution. Okay, so this is pretty interesting. All right, well, we talked about the results. So what about example 7? It says, in Dallas, Texas, about 37% of the days are clear. And to define what it means to be clear means that clouds cover less than 30% of the sky during daylight hours. Okay, so again, we want to find the mean variance and standard deviation for the number of clear days per year. So we'll do this one exactly like we did the last one. So the mean, or the expected number of clear days in any randomly selected year in Dallas, Texas, is going to be the number of trials. In this case, guys, you would think 365, right? Because there's 365 days times the probability of success, or in other words, the probability that the sky is clear. Okay. And so this one, you need the calculator for. we get, I'm just going to say 135 days, okay? So roughly 135 days, that would be the average number of clear days that you could expect. And then the variance would just be 365 times 37% times 1 minus 37%, which is 63%. Let's see what this gives us. Well, I've already got that in there, so now I could just multiply it by 0.63. Okay, so 85.08. And again, this is technically in square units. So this doesn't make much sense to us, so now we're going to find the standard deviation. So if I take the square root of this number, this would give me the average amount of variation, 9.22 days. Okay. So again, with respect to this distribution being symmetric and bell-shaped, what we're going to call normal later on, you could expect about 68% of the time that the number of days in which it's clear in Dallas, Texas for a year is this value plus or minus one of these standard deviations. And then 95% of the time, you could expect this number of days plus or minus 2 times this value, okay? It would be clear. All right, so let's look at one last thing real quick. Graphing a binomial distribution. Well, we sort of saw one up here, okay? Although, as you can see, my bars had gaps in them. Typically, these will not have gaps because the value of x can't be any value between 0 and 1. Remember, this is not a continuous random variable. It's discrete. That's why there really shouldn't be gaps. But Excel, I haven't figured out how to do it without gaps. But anyway. But here's some examples right here, okay? So what happens is, depending on the value of a success, or the probability of success, that'll tell you how symmetric the distribution will be, okay? If the value of success is low, you're not going to expect the value of x to take on many of these low numbers if x is counting the number of successes, okay? And then if the value of a success is high, then you're going to expect x to actually take on more of these. Well, I think I'm pointing at these backwards. You're going to expect x to take on more of these higher values instead of these lower values, okay? Yeah, and so because of that, depending on the probability of success, that will render these distributions either roughly symmetric or left-tailed or right-tailed, depending on that value, okay? So what we've got going on here is we've got 3 binomial distributions. So this one is very similar to the one I did. And the number of trials in each of these is the same. But the value that that x can assume ranges from 0 to 5 in each of these. Okay, so evidently there were only 5 trials. And so the values for x could be anywhere from 0 all the way up to 5. And so these are the distributions of, well, these are visually the distributions of a probability distribution like this, okay, where the heights of the bar correspond to the probability that x is each of these specific values. All right, and so what happens is, whenever the value of a success, or the probability of success, is rather low, you're going to expect more low values from your random variable, okay, as opposed to higher values. So you're going to get a right-tailed distribution. Most of your probability is going to be on the lower end. Okay, so I'm going to label this one P was probably 0.25 here. And then whenever you have most of your probability for higher values of x, that corresponds to a higher probability of success, right? Think about the LeBron James example. If LeBron James is a 70 or 80% free throw shooter, you're going to expect him to, if he's shooting 10 free throws, to hit 7 or 8 of them. Those are going to be the most likely outcomes. Okay, so this would correspond to 0.75. And then whenever P is close to 50%, most of your probability is going to lie right in the middle. And the reason is because if you're expecting as many successes as failures, you're looking at 50-50 essentially, right? If you toss a coin 10 times and the probability of getting a heads is 50%, then you would expect to get about 5 heads, roughly 4, 5, or 6. That's where most of your probability is going to lie. And then for values of x, on either side of those, you're going to see decreasing, symmetrically decreasing probability. And so that's why we would get a distribution that looks like this. Okay. This one is symmetric though, the other two are not. They are skewed. Okay, this is a left tail distribution, this is a right tail distribution, this is a roughly symmetric distribution right here. Now what happens if we keep the success rate the same but increase the number of trials? Well, if the number of trials increases, then that means the number of values that x can assume will also increase. And so what that means is that if you're looking at a probability distribution, you're going to have more bars corresponding to the more values that x can assume. Okay, so this one right here, we've got probabilities associated with values of x all the way up to about 12 right here. So this would correspond to n being 12. And then this one, it looks like most of the probability stops right around here at 4. That appears to be the highest value that x could assume, 4 successes in 4 trials. So here n would probably be 4. And then in this last one, guys, n would be equal to 8. Now, I can't remember if we talk about it in this course because I haven't taught it in a little bit, but as you let n continue to increase in value, you get more and more bars, and furthermore, the shape of that distribution tends to look more and more like that bell curve. Okay, the increased number of bars cause the outline of the shape to become smoother and smoother and smoother. And so there's a theorem, or there's a consequence of that says that if p is exactly 0.5 and you let the number of trials approach infinity, then you'll actually get what we refer to as a normal distribution, a perfect bell curve, okay, not just an approximate. But anyway, that's all for now, and that actually is the conclusion of Chapter 4. In Chapter 5, guys, we're going to be talking about continuous random variables. So a random variable that can't just assume discrete values like 0, 1, 2, 3, 4, etc., but can assume infinitely many values. Remember, like a piece of the number line. Remember, like, for example, the amount of gas that you pump into your gas tank. If it's a 12-gallon tank, there's an entire interval there of values that it could assume, anywhere from 0 to a maximum of 12 gallons, and every single value in between. Not just discrete values like 0, 1, 2, 3, or 4. Okay. So anyway, we'll look at that in Chapter 5.